How can an autonomous quadrotor identify and inspect interesting features in an unknown environment? The most obvious approach to solving this problem would be to first map the environment and then look for interesting features. Michigan Autonomous Aerial Vehicles is competing in a competition where teams must build an aerial vehicle to enter and navigate an unknown environment. The vehicle must find and enter the environment through a window, identify interesting features, retrieve a flash drive located on a table, drop off a decoy flash drive, and exit the building in under 10 minutes. An immediate challenge is, how does the quadrotor identify features like windows and tables? Finding a table may seem like an easy task, but doing so requires a full 3D map of the environment. Constructing a detailed 3D map using conventional methods presents a problem. How does the vehicle store its map of the world? An obvious method would be to divide up the world into equally sized bins. These bins are either full or empty based on the objects in the environment. This process is known as rasterization. However, the memory required to represent this map of the world grows proportionally to the size of the world. Most small autonomous robots have very low computing power, and at high resolution, these traditional techniques require more memory than the robots have available. In other words, grid-based world representations become far too resource-intensive in 3 dimensions. To solve this problem, we employed the use of Octrees. Octrees are a way of representing data in 3 dimensions using less memory than standard grid-based techniques. Octrees are tough to visualize in 3 dimensions, so we'll explain how this technique works in 2 dimensions first. Let's envision a world represented by a grid. We've erased the grid lines for visualization purposes. At first, the robot starts off in an empty world. As the robot sees objects in the world, it adds them to the map, filling in the boxes where the object resides. Each object is rasterized into the grid and reduced to a small number of boxes. Now envision the same scenario, but instead of the grid-styled map, picture a world represented by one big box. Initially, the robot starts off in this box. Again, the robot observes an object, and again, the object is added to the map. But how do we represent the object when our whole world is only one box? Do we fill the whole box? No. We split that box into 4 smaller boxes, and then split them again, and again, until we have enough resolution to represent the object we've observed. Notice how we only split those boxes that contain the object we're trying to represent. The Oct-Tree approach represents empty space with larger, less memory-intensive boxes, while interesting sections of the map like walls, tables, and other obstacles are represented as high-resolution groups of small boxes. The reduced number of boxes allows us to represent the world using a fraction of the memory. Although randomly accessing a point in the world becomes slower due to the structure of the Oct-Tree, methodically traversing the map is quicker than traditional grid-based techniques. This allows us to search through the map faster for planning and identifying interesting features. Let's say the interesting features we're looking for are tables. We first start by finding full boxes that can possibly be part of a table. The box must not have a full box directly on top of it, and it must have at least 2 full boxes next to it. This effectively sorts for flat surfaces. We then group the potential table objects that are near each other. Clustering the previously selected boxes is simple given the Oct-Tree structure. Once clustered, we further filter for table-like structures. If the cluster has at least a minimum width and depth, contains at least a minimum number of boxes, and is high enough off of the ground, we consider it to be a table. Once we find a table, our quadrotor attempts to fly over to that area to further inspect the table. We use our Oct-Tree map again to navigate through the 3D environment. This reveals one of the biggest advantages of using Oct-Trees. Since open air is represented with large singular Oct-Trees, planning algorithms have far fewer routes to inspect. In other words, planning from A to B may only require traveling through one Oct-Tree. This drastically speeds up the whole path planning process. The end result is a navigation system capable of finding tables and navigating through complex terrain while remaining efficient enough to run on the quadrotor. Thank you for watching. If you need to contact us, please do so at the email addresses listed below.